This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
No, I thought because another student came, he's applying to Hong Kong University, so I told him I'll give a reference. Yeah, I thought that maybe this is also. Yeah, here they usually they want to see the name. They don't ask. Yeah. They might call me if required. Usually they don't.
Okay. So my research project is about optimization, trajectory generation, something like that.
Good. Yeah.
Thank you.
Thank you.
Because you cancel Tuesday and Thursday workshop, but Friday is public holiday.
No, but I think we don't have the holiday. I think so. I will check with our people.
Just put up the university calendar, and apparently we do get the day off.
Okay.
So Friday is public holiday.
Yeah.
So how many labs do we have got on Friday?
2.
Yeah, I think this week I think that's a bit difficult. What we can do is I will put it on the LMS. Please join one of the labs.
But just 2 workshops left. Just Wednesday and
Okay. But then what we can do is, because after that is sort work, I'll see Thursday whether we can find some time. Because anyway, this week we don't have anything serious. It's kind of distributing the kit, soldering kit, just for practicing.
So only for solder, we could always do the through the MSc tools training. Tom Harper runs the learning to solder classes.
Anyway, I will check with our teaching office. Yeah, usually they should be sorting out these issues. Anyway, I will check with them. Yeah, thank you for letting me know. Okay, so we are back and I've already got some answers, good answers. So what do you think? So our repetition is 1 kilohertz. So how many of you think more than 1 kilohertz is sufficient? So how will you find out? Because if you are putting 1 kilohertz, what will happen? Suppose your bandwidth is only 1 kilohertz, your amplifier. Yep. Then, so what is the approximate bandwidth you will be looking at? So that's the reason I already got the coffee winners. Maybe you have to drink the 2 coffees. Then we'll buy you 2 coffees. We'll buy you 1 coffee. Then who is the third one? I forgot. Yes, and yeah, you have to drink 2 coffees. So you can call maybe one of your friends. Yeah. So I give you the option. You can call maybe your friend because you can't drink anywhere 2 coffees. So these guys, make a friendship with these guys. They got a coffee coupon. So you can invite your friend. So that is the reason we are going to study rise time, because here you can see this is an important question. Sometimes you may encounter this. This is not a fancy question. This is a real question. Why? Because sometimes from the laser you are going to get 10 nanosecond pulses, and then that pulses are going to hit maybe some surface and then coming back. Then you may be putting a photo detector to detect that pulse. Then after that you need to design an amplifier. Then you might think repetition is only 1 kilohertz, because the separation between 2 pulses, that means 1 kilohertz, that is equal to 1 millisecond. But then the pulse width is the matter that will decide the bandwidth. So bandwidth, the straightforward, if you got a sinusoidal signal, so sinusoidal means see, like this. Sinusoidal, if you take a Fourier transform, then you will be getting 1 frequency components, like 1 frequency components here, another one here. So if it is 1 kilohertz, so you get here minus 1 kilohertz, here you are getting 1 kilohertz. So you are getting only 2 frequency components, means just 1 kilohertz. So when you take FFT, you got only one frequency, and then that is fine. So you can get a 1 kilohertz bandwidth. You can amplify this sinusoidal signal. But here, this is the here also see, but the point I am making is here the repetition or the period is 1 kilohertz. But here that is a bit different. Here this is a pulse. The separation is 1 kilohertz. Please don't confuse with the period of the sinusoidal wave. You know what I meant? So that's the reason the confusion comes. Because here this is a sinusoidal wave, the period equal to 1 kilohertz, and then when you take a Fourier transform, you are getting only 1 kilohertz, only one spike, only one frequency component. And then for this one, it is easy. You see what is the time period, 1 kilohertz and or 1 millisecond. Then you need a bandwidth, maybe 2 kilohertz or 1 kilohertz also you can amplify. But here the repetition is 1 kilohertz, but then it is not a sinusoid, it's a pulse with a width of 20 nanosecond. So if you are taking a Fourier transform of this one, if you take a FFT, then you will see so many sinusoidal components. So many high frequencies means so many sinusoidal components are coming together, then you are getting 20 nanosecond. Then in the FFT, what you will do is FFT, so you will get so many frequency components you will get like this. So these are the frequencies. So here you get only one, here you are going to get so many frequency components. And so it got so many frequency components, then we define a term called rise time. So we haven't studied that one, rise time. So rise time means when you have a pulse or a signal like this, any signal, so this may be 0 and then this may be 1 volt. So from here to here, so they call it as rise time means this is a 10% of the voltage, this is a 90%. So the signal that is rising from 10% to the 90%, how much time it is taking. So this is the time. So this time is called a rise time. So we define a time called rise time. So this time, how much time from 10% of the signal to 90%, that is called rise time. So then this rise time we can measure on the oscilloscope. When you have a signal, we can find out the rise time. In some scope there is a button, you just press rise time, it will tell you the rise time. Or you can use you just put the cursors and then you can measure the rise time. So once you know the rise time, then there is an equation called bandwidth. Bandwidth equal to 0.35 by TR. So TR is the rise time. So bandwidth you can find out using this standard equation. Again, derivation you don't have to find. This is a equation, is a standard equation we can derive from discharging capacitors. But then again, you don't have to use the derivation. But this equation you should be remembering. Bandwidth is approximately equal to 0.35 by TR, rise time. Yeah, some of you said the answer, the bandwidth here is equal to approximately 1 by 20 nanosecond. Yeah, that also you can approximate. But bit more accurate way is bandwidth equal to 0.35 by TR, rise time. And then, so here how much it will come? 0.35 by rise time. So here I haven't given any voltage. Yes, I gave you 0 to 20 millivolt. So maybe from here to here, rise time is around maybe 8 nanosecond, because this width is 20. So around 8 nanosecond is your 8 nanosecond. So which is equal to 0.35 by divided by 8 into 10 to the power of 9, because nanosecond is minus 9, it will come up. So how much is this one? Approximately equal to 40. So this will be point. No, it's not point. You need a. So this will become 0.4 into 10 to the power of 9 approximately, and then that is equal to 4 into 10 to the power of 8. You are right. Yeah, 40. Sorry. Yeah, that is 40. See, that's how we calculate. So we have to look into that rise time. Then question for you. So here it is 40 megahertz. So if I am getting 40 megahertz here, that is a minimum requirement. Then I will get the amplification to 200 here, because the 10 amplification, then the pulse width will be around 20 nanosecond. Suppose I am going to use 40, not 40, I am going to use 20 megahertz. So if I am going to use 20 megahertz, what will happen is, as I said, then you will be taking off some of the high frequency components in the amplifier. And then what will happen? If you are removing some high frequency components from a pulse, what will happen to the pulse? Or in other words, so this is your pulse. So when I take maybe nanosecond width, so when I take FFT, so I am getting so many sinusoidal, so many. Then I am going to take some out, and then again I am doing an FFT back. So what will happen to the signal? How many of you think it will become more sharp? So when you take off some of the frequency components, this will get spreading. It will get spread like this. So when you add more frequency components, only it will become very, very narrow. So if you are removing some frequency components from that, it will become a bit more spreading. Then if you are using 20 megahertz here, what will happen is you will get amplification. Then in your case, what will happen is, so your pulses are 10 nanosecond width, and then this separation is 1 kilohertz or 1 millisecond. Then your amplifier into 10 magnification, sorry, not magnification, amplification, and you are using 20 megahertz. Then here what you will do, you will definitely get 0 to 20 millivolt. Then here you will get amplification, but then you may not get 20 millivolt. You may get around maybe 15 millivolt. But then you will see something like this. So this might become maybe 25 nanosecond or even 30 nanosecond. This might become 30 nanosecond, the width. And then this one is still 1 kilohertz. So the amplification will reduce when you don't have enough bandwidth, and also there will be spreading of the signal because you don't have enough bandwidth. So some of the frequency components are removed so that the pulse will become spreading. So that is the important concept. As I said, because we got lasers, even we got laser operating at femtoseconds. Very narrow pulses are there. So that bandwidth then you are calculating based on the rise time. So ability of a digital system to perform at a given frequency is dependent not on the operating frequency but on the rise time. See, not on the operating frequency means when you have pulses, the operating frequency, the repetition is only 1 kilohertz, but then your rise time is in nanosecond. So that will decide the bandwidth. Rise time is the time it takes for the signal to change from 10% to 90%. So that's the reason this is the rise time. Approximate frequency you should be designing is for the knee frequency. So the knee frequency is 0.35 divided by TR. That is a knee frequency, or that is a bandwidth required. So that is an important concept. So that's the reason I discussed it a bit more in detail. Then another concept is terminations. A signal traveling down an unterminated wire will reflect doubling the voltage on the way back. So what will happen is when you have a high frequency signals, and then the high frequency signals will be propagating, and when the impedance is suddenly changing, the signals will reflect high frequency signals. So then you should have proper termination. So proper terminations means in low frequencies these things are not an issue. Even in your DSO, though we call it as 40 megahertz clock as high frequency, actually that is not very high frequency. So these issues will come when you have 1 gigahertz and above signal, 1 gigahertz and above. So what it says is this may be your copper track. So this is your copper track is like this, and then you can design this copper track for 50 ohm. We are going to discuss how to design it. So then this is IC. From the IC you got 50 ohm impedance, and then this track is 50 ohm. And then the high frequency signals are coming like this. You got a high frequency signal, maybe it's a pulse, like this sharp pulse. And then again you are getting another sharp pulse like this. Then suppose it is open, and then here suddenly you are connecting some resistances. Here one resistor that is equal to 1 kilo ohm, and then it is going to another IC. Then what will happen is this pulse will come here. When it is experiencing an impedance change, it will reflect back from here. And then what will happen is when you put your oscilloscope probe here, depending upon this mismatch, you will see not a pulse, then you will see something like this. Some ringing and then coming like this. Again you will see some ringing and then coming like this. See, multiple things will, so that is because of the reflection. So that is called reflection. Most of the time we call it as a ringing. So you will see some ringing like this, and then so this can be avoided when you match this 50 ohm. If you replace this with the 50 ohm, then you will see, then when you measure it, then you can see some kind of a clear signal again, something like this. So then you need to have proper terminations, and even in high frequency board we will not keep any copper track open, like one signal is coming and then we will not keep it open in high frequencies, because then if you got some other pad here, then it will be forming a capacitor between these two in the high frequencies. So that's the reason we will not keep it open. So we have to put proper termination. Reflection and termination. PCB tracks are transmission lines. So if you study the transmission lines theory, all the PCB tracks are transmission lines. So signals reflect when they reach the end of a line. Correct termination will ensure signal doesn't reflect. To stop reflection, terminate with a resistor of same value as the line impedance. That's what I have shown. When you have 50 ohm impedance, your track is 50 ohm impedance, you have to put a resistance from track to the ground 50 ohm. Easiest way to modify impedance is by changing the track width. So if you can change the track width, you can vary the impedance, and we will study how. See, this is a basic strip line. Means this is your FR4 board, and then somebody will ask you, my PCB track should be 50 ohm, because you are going to put all the ICs and the IC output impedance equal to 50 ohms, and then you are going to operate maybe at a very high frequency. And then somebody will ask you, because now you designed your PCB and then you know how to design the PCB, you know how to calculate the bandwidth, and then you know how to make a system. Then in some companies they will ask you, oh, design a PCB, we want 50 ohm track impedance. You know what I meant? Then when you say 50 ohm track impedance, then you should be thinking, I never designed a 50 ohm track impedance. It is very easy. Then you can use this equation. So this is a standard equation. So this will give you the impedance of the track, copper track. So Z0 should be 50. So the standard equation is 87 divided by, 87 is a constant, epsilon r, that is a dielectric constant. Dielectric constant of your FR4 board, you can get it, it's a standard value, plus 1.41 into logarithmic value of 5.98 into h. So what is this h? Dielectric thickness. See, the thickness of your FR4 board divided by 0.8 into W plus T. W is the trace width. See, you can vary the width of the trace, you can vary the thickness of the trace, and then you can tune it. Then here in a company, they might tell you, we only got this FR4 material, or a supplier will tell you, our FR4 material got dielectric constant is this much, and then we have got a thickness, standard thickness is maybe couple of millimeters. Then you don't have to worry. Then you put in, so this one is a constant, then height of the dielectric, that is also constant with a supplier, but still you can get this one 50 ohm. How? You can vary the width and the thickness. Then again you can keep the thickness constant for all the designs. Then you vary the width. Basically by varying the width, you can get 50 ohm impedance. Then why I don't want to change the thickness. Why I want to change the thickness is in the same board it is very difficult to get a different thickness, because you are depositing the copper plate. So then you can keep the thickness constant, then the dielectric height constant, you vary the width. Usually that's what we do. Then we can get for 50 ohm. So if you design for 50 ohm, you will get 50 ohm. Then you can design for 75, you can get 75. So that's how we will be designing a 50 ohm impedance. This one is required for high frequencies. In your DSO, we don't need a 50 ohm, because you are operating 40 megahertz is not a high frequency. And so that's the reason. This is applicable for RF, radio frequency, or very high speed, like if 1 gigahertz, then you need a impedance match. Impedance match means your IC will have output impedance, maybe some value, and then they will say that this should have an impedance matching transmission line. the data sheet will tell you 50 ohm you need to design your PCB. Then you will be using this one, this equation. Then sometimes there will be differential lines. As I said, where differential lines are coming, because some ICs got a differential output. Because see, this is one, so in one case you got this is IC, or it's simple an amplifier. So in some amplifier you got only one output, and then the copper track we are going to make 50 ohm. But in sometimes you got some amplifier, then you got dual track. So this is the output. So when you have dual track, what will happen is means when you have a signal like this in the dual track, then here the signal will be just opposite of what you connect here, like this. So these are complementary. So when it is like this, then here it will be like this. So these are differential line. And then when you have this type differential one, then the equations are different. So when you have a differential strip line, see these are the two tracks, then your equation is a little bit more lengthy. But all the values are again depending upon trace width, trace thickness, and trace separation. Only that separation is coming into picture. But then differential, you will not be designing differential until and unless you are making some communication board. Then you may have a differential line. Otherwise, most of the systems you will be using only this type, single-ended one like this. Only in some communication board, in communication ICs, they have this type differential lines to suppress the noise, differential. So that's how we will be designing impedance. Track length matching. So signals do not arrive at their destination instantaneously. So this track length, in your case you will be putting track maybe around the IC and then putting a via, putting another one. But then this length of the track is a problem when you are designing a very high frequency very high frequency board. Why? Because when you have a 1 gigahertz frequency, then you are going to the nanosecond regime. Then you have got two signals coming, some pulses coming, both got maybe 10 nanosecond pulses are going two places. But then if your track is a bit curved, one path will take more time. But in your case also, what I am talking about is, maybe I should draw it. See, this is one IC, so this is a digital IC, and then you got one signal. So this signal is coming like this, and then for time being case 1, so the width of the signal, the width, that is W. In case 1, it is equal to 1 millisecond. And then, so this is a signal S. Then you got a reset. So reset also, you are deriving, so this one is, so reset signal is coming. So that also got W, same W. Then, so our requirement is first S1, the first signal should come, first reset should come. So first reset signal should come, then second one is, then only your signal should come. So that's our requirement. So this first reset should come, and then second signal should come. So reset comes, and then all your output pins are cleared, then your signal should come. So first reset, and then second signal should come. Then this is the W. In first case it is equal to 1 millisecond. So if this is the case, if you are operating, see this is 1 millisecond. So this 1 millisecond is approximately 1 kilohertz. So it's a low frequency one. In this case, if you want to make, and then you are, so these signals are coming at same time. Almost same times, somewhere it is coming. Then if you want to make this first and then this delayed, then most of the time you will be using a delay line. So delay circuits are there. You can buy delay ICs. So they can delay your signal little bit. So then you will be delaying some here, maybe some millisecond or something, you can delay it. And then what will happen is this signal, because this signal is the same time it is coming, so then this will come, and then later only this signal will come. But When in the second case your W width is going to be 10 nanosecond or 10 nanosecond, then what will happen is you don't need this delay IC or anything. In that case, then what you can do is, because now it is in nanosecond time, so nanosecond time, then the advantage is so this is your signal and then this is your reset. Then how you will do is first you get a reset, then you get signal. Though these signals are coming same time from here, these signals are coming same time, t equal to 0, it is coming same time, but then you want to first reset going, then only signal should come. But when you have nanosecond time period, then what you can do is you don't need this delay, so you can make this one a little bit curved like this, so at the same time the signal is coming. So t equal to 0, t equal to 0. Then because of this curvature itself, this signal will get delayed when it is 10 nanosecond, because this curvature is maybe a few centimeter, but then that is enough to create a nanosecond delay. You know what I meant? So by just bending the PCB track, you can get delay if you are operating in very high frequency, like in gigahertz frequencies. But then if you apply the same principle for 1 millisecond, nothing will happen, because this delay is going to be nanosecond, your signal is in millisecond, so that will not work it. So there are other issues. Signals do not arrive at their destination instantaneously, maybe due to some reason. When high precision timing is required, having an accurate track length is essential. So that is the reason the track of the length is essential. So another example, maybe this will make you understand a bit more. See, you got a differential signal, and one signal is like this, and then another signal here is like this. So both are going to another IC, and then this is the input pin. And then case 1, your W equal to this width, 10 millisecond. Case 2, W equal to 2 nanosecond. Then when you are designing the PCB, so when you design the PCB, what you did is, because you got some more components here, you made a bend like this, and here you got a straight line like this. Okay, so in the case 1, 10 millisecond, both the signal will come here at the same time. So t equal to x, then t equal to t prime x second, both will come simultaneously, maybe a little bit, because this will create only maybe 1 nanosecond delay, this part, and then 1 nanosecond plus 10 millisecond is nothing, so that you don't have any issue at all. But when you have this 2 nanosecond here, then what will happen is this nanosecond will add. So you got 10 nanosecond, then these two signals will not reach at same time. So this one will be delayed by 1 nanosecond. This will be arriving at t equal to, then it will become t equal to x second plus 1 nanosecond. Here t prime, that is a t prime t. So this is a time t, this is a time t prime. So t prime equal to x second. See, this will come correctly here, but then the other signal, complementary signal, will not come correctly because of the 1 nanosecond. So high frequencies, you have to make sure that your track, if it is a differential, precision timing is required. Having accurate track length is essential. So that is one situation where you need accurate track length. Again, we don't care if you don't have differential line, and if you are not operating at very high frequencies. By adding some bends into the track, that's the reason I said the PCB track length can be matched to ensure signals arrive at the same time. If you got some issue, you can play with the bending of the track. You can make the length. Tools, interactive length tuning in Altium, designer and tools either side. See, you got some tools for high frequency design on Altium. Something like this, see. So propagation delay. So if you want to create some delay, then you can make bends like this. So this is an example. Assuming clock pulses arrive at the same time to all the components can be sometimes hazardous. You need some kind of delay. For example, if you want a reset coming first and then signal coming. And clock distribution is an important issue at high frequency. So if you want to delay one signal, then you can put something like this bend. And then this will be delayed. This may be your reset. Then this may be your signal. And if both are coming at same time here, but then here it will be delayed because of this bend. But this is operating, maybe I will say this is applicable only at gigahertz frequencies. If you use your kilohertz signal, you are not going to get any delay, because you are getting delay, but then it is your signal already is in millisecond. If you get 1 nanosecond delay, that is not going to make any change. Crosstalk. So near and crosstalk, people sometimes call it as next. Interference between two pairs in a cable measured at the same end of the cable as the transmitter. Appropriate source termination reduces next. Means when you have some IC and then there could be crosstalk between two lines, between two pairs, and then when you are measuring at the transmitter side, so that is called a near end crosstalk. Far end crosstalk is the interference between two pairs of a cable measured at the other end of the cable. Because if it is starting from one side, from here, the IC it is starting from here, then it is called a near end. If you are measuring on the other end, it is called a far end. Then alien crosstalk, not because of the aliens, caused by other cables routed close to the cable of interest. That is because other cables routed close to the cable of interest, maybe due to some other piece, so maybe I'll draw it, then it is clear. So near end means, so you got an IC, then two tracks are coming from here, and then near end means you measure the crosstalk at this point, and then this, because of that signal is changing here, this it will induce an EMF here. That's kind of coupling. So here signal is changing, it will couple here. So that is a near end. Far end means when you measure here, that is a far end. If you are measuring this side, it is called a near end. Here it is called a far end. Alien means you are putting some other track here, and if some changes, it is coupling here. So that is called due to some other track, not from the same IC. So that is called alien crosstalk. So cancelling far end crosstalk. So when you have far end crosstalk, that is away from your IC, means input of some other IC. When high frequency signal induces crosstalk on a parallel track, which I have already shown. So consists of two components, capacity coupling, which induces a positive spikes that propagate away from the wavefront. Yeah, so sometimes you will see some kind of interesting phenomena. So one is, as I said in the drawing here, so this is a connection, and then you connect it, and then you don't have this one. So you got to do these things. Two lines are going. Then when you measure it, and then what will happen is, so you will see sometimes a positive spike like this away from the wavefront. So you might be seeing some waveform, then you will see some positive spike somewhere, it will be moving like this. You may see sometimes in high frequency when you are measuring. So that is due to capacity coupling. And then if it is a negative spike like this, it is moving, then it is due to inductive one. And so when you put correct termination, you can avoid those things. Means you got a clean signal, you have designed a high frequency. So the summary is the following. So you have designed a high frequency PCB, and then you mounted the components, and then you are monitoring some clock. Then you know that the clock is fine. But then when you monitor, you connected on another IC, then you see some issues. Some spike is coming, something is moving, then that is due to termination. Because the clock was there, everything was fine. When you connected the second IC, the problem started. And then something is going on with the termination. Then from the spike also, people can identify sometimes the debugging. Some spike is going, experienced people will tell, oh, this is the issue. That some spike is going in the forward, it is due to capacity coupling. Or it is going in the opposite direction, negative, then it is due to inductive coupling. So these are some, it means when you get experience, you will be able to figure out what is going on. So again, it is for high frequencies. Why I am teaching high frequencies because outside is high frequency. When you go out, people are designing high frequency boards. And pin swapping. To optimize your PCB layout, sometimes you can move pins around. So can you please tell me one place where you can move pins? In normal ICs, you can't move pins around. Yeah, even in microcontroller, you can move the pin, you can decide the pin. And PCB design does not need to be a one-way process. You can start laying out your PCB, then go back and change schematics to simplify the layout, which you are doing. Then pin scapping, RAM, microcontroller, FPGAs, all these places, you don't need to be you can decide the pin configuration. Yeah, Altium Designer supports pin swapping. Tools, pin / part swapping. So you can, there is a tool. You can swap the pins. High currents. So sometimes you will encounter high currents. So when you have high currents means not in milliamps. Usually if 2-3 milliamps is not high current, close to 1 amps, more than 1 ampere. So these are the high currents. Large currents cause track heating. So if you are pumping 2-3 amps, then the track will be heating depending upon the cross section area and the length of the track and the location of the track. When it is impractical to make track any wider, you can remove the solder mask off the track and add solder to thicken the cross section. So sometimes what you can do is you are pumping maybe 2 amps, and then you can increase the width, the track width, and then you can reduce the heat dissipation. But the problem is you can't make it further wider. Then you will have a PCB with a big track. So you don't need to do that one. Then what you need is, so you have to think logically, your track is getting heated when the current is flowing. Then one way to do is, maybe you can connect this to a big pad here, so that you are increasing the dissipation, the heat sink. Another thing what you can do is, as they said, because you got the solder mask, the heat is not radiating, so that your PCB might get hot. You know what I meant? Because you got the track, then you increase the width, and then because of the solder mask, the PCB is getting hot, but then it is not radiating because of the solder mask. Then you can cut the solder mask, and then they said then you can also put a little bit solder on the top, so that you are increasing the area. So when you increase the area, it can radiate more. So people have done that one. It will work. Then open the solder mask, just draw lines on the solder mask layer. So in one place where I have encountered this issue, because I got a surface mount IC, and then that IC, they already said that power dissipation is very high, and that started heating up. But then what they did is, then what we did is, we put the IC on the we put the IC on the PCB. Then before we designed, we put a small pad underneath the IC, and then we put a via and then connected on the other side, and then this side we connected to the ground plane. Then the IC got heated, then that heat is connected to this small pad. That small pad, the heat came through the via to the big ground plane. You know what I meant? Because the area is more, it started radiating. So that sometimes you can do that one if your IC is getting hot. This is for the track. To open the solder mask, how will you open the solder mask? Just draw lines on the solder mask layer. So you can just maybe you can use a small knife and then cut it. Yeah, usually some of you will be cutting your track. I will come and see. Yeah, you can cut the PCB. So when you cut it, you should be cutting like toys. Not one cut may be not good, but still you may have the connection. So make sure that you cut toys. And then again, if you want to solder to the track, then you may have to remove the solder mask and then put the jumper. No, I'm not joking. I have seen DSO working with the jumper because the connections were having issue. And yeah, another thing. So when you are a design system engineer or electronics engineer, it is easy to design a system. But then you need more knowledge in debugging than designing. You know that one? Design means you got the design specification and you read the data sheet, you have the system knowledge, then you design it. Maybe some part you simulated. But when you test it, you will see many interesting things. But in order to sort it out, you should have good knowledge actually. So debugging people got more knowledge than the design engineers. So the design engineer will be a debugging engineer after getting so many years of experience. So like when I designed, like whenever we had issue, we call the senior engineer and he comes and say, oh, that's the issue, then that's the issue. Yeah, we also learned that bit of experience. So that in order to avoid in your DSO, we are designing it for the first time. So that's the reason we will be uploading a video on LMS. And then you can see after each stage what is expected signal, so that you can also debug your DSO. So that it definitely helped last year students. The year before, some students got the right signal, but then they didn't understand that was the right signal. So if your board is not working, I think that is the best opportunity to learn the DSO. Why? Because when your board is not working, you will come back to the schematics you will come to the block level diagram and understand what is happening, what signal I am missing, then you will learn actually more. So if your board is not working, actually you are lucky, because you are going to learn a lot. No, I am not joking. Suppose you are designing an amplifier, operation amplifier, you designed it, you mounted, you got the signal. You learn nothing. You connect the signal, but somebody's amplifier didn't work. Then they will be reading, they will be putting some oscillation came, they will be studying about the feedback, and then they will sort it out, they learn a lot. So if you are unlucky, your DSO will work without any issues. But if you are lucky, your DSO will not work, and then you will understand the system, put some jumpers, and then your DSO make it working. So that DSO we will give you 1 or 2 marks more than straight away working, because we will understand the difficulty, how you made it working. So that is the reason we give you mark even if you are putting jumpers and then make it working. We will ask you some questions. So then if you can answer why it was not working, how you made it working, definitely you got more knowledge. So that is the reason debugging doesn't mean that you get the DSO, you make some cut the track and make it not working and then you put the jumper. Don't do that one. So large currents cause track heating depending on the cross-section area and length of the track, which we already discussed. So designing for manufacturability. So this is a big issue when you want to make many numbers, huge area, couple of lectures in itself. So this itself is a design for manufacturability is a big topic. Try to minimize the processes, try to keep all the components on one side, add test points, follow the manufacturer's suggestion. So when you make it, because your DSO is not for mass production, suppose you are making your DSO for mass production, there are some people, they will be looking into how can we mass produce. Then first thing they will be looking is, can we use pick and place? Whether your design, you can make pick and place, then put all the components on one side so that the fabrication cost will be less, because pick and place machine can put it on one side. Then no, you don't need to turn it. Then another thing is minimize the processes. So they will try to avoid the number of processes because that will increase the cost. Then they also add test points. How many of you added test points in your DSO? Yeah, very good. Because if you don't add test points, how will you test it? Obviously you can touch the track, but it's better to add some test points. So in the companies, when you design some board, they will how they will say that your board is working. Because after this machine is soldering, machine is putting the components, then reflow oven, then it will come to a testing person. Then he is not going to test everything. He will only test some test points provided. And then that's how they say it's okay. So they will the engineer will say only test, in your case DSO, they will test the output of the amplifier, output of the maybe filter, then ADC, DAC, some couple of points they will say, and then the testing person will say, okay, test only 5 points. So if these 5 points are working, the system is working, and then they will put the test point. So when the PCB coming out from the machine, then one person will be testing and then they will say, yeah, tested, okay. So that's called test points, you have to put it. Then follow manufacturer suggestions about the location of the components for particular soldering process. Then decoupling capacitors. So circuit switches requires large current suddenly. So decoupling capacitors close to ICs provided this, then should minimize inductance between the capacitor and each device. Then in 4-layer board, so in a 4-layer board you can make a capacitor using the PCB. Why? With a voltage and a ground plane provides a large capacitor as a part of the PCB. Because if you got a 4-layer board, this is voltage, this is ground, then you are getting a capacitor, very big capacitor here, because this is FR4 material. You know what I meant? If you got a dielectric multi-layer board, you can make use of this layer for a capacitor, because here you got a voltage plus 5, this is ground, and then this is separated by a dielectric, so it's a capacitor. So that also is possible. Some people use that one, that design for making a capacitor when you are making a multi-layer design. Means again I have shown you, because when somebody might tell you where is a capacitor, then somebody will say I used a capacitor in the PCB. Then you might be thinking maybe this person did not get a degree in the PCB, but then you can make it, because capacitor is 2 plates separated by a dielectric. So here you got a 5 volt, and then here if you got ground, yes, this is a capacitor actually. So PCB capacitors, inductors and antennas, yes. So this is also included. Then you might think again we are not doing anything with this one, but this information is required as a system engineer. People make capacitors, inductors, antennas using PCB track. Like then somebody will ask you, have you seen my antenna? Antenna, at least you know that you can make with a track or on the copper. Then somebody might ask you maybe, have you seen my capacitor on the PCB? Then you will be asking, looking at, you will see some track. Then you will see which capacitor, what capacitor are you talking about? Or inductor, have you seen my inductor? Then again you will see only some tracks. Yes, it is possible to design capacitors, inductors and antennas using the PCB track for high frequency application. Again you will see these things in the radio frequency, RF frequencies in gigahertz. Sometimes it is easier to construct an inductor, capacitor, antenna on a PCB. Taking into account the PCB's dielectric, accurate devices can be constructed on the PCB without increasing the cost of the device. Values can vary due to variance in substrate thickness, dielectric used, thickness of the solder mask. Antennas on the devices such as 802.11 are often printed straight into the PCB to save money. So example, microstrip components. So there is going to again RF radio frequency electronics. They will be using high frequencies. It is possible to create components on your PCB such as capacitor, inductor, filters, delay lines, transformers, antennas. You can use maybe using a track. See. Then before going that one, we will discuss about the discontinuities. So we can make these things. In order to understand this one, at high frequencies, what will happen? So if you are designing, suppose from your IC, your signal is coming, then you put W1, then immediately you made your track width, you reduce it like this. Then you got a junction here, that is T. If you are operating at low frequencies, again 1 kilohertz, this is not going to affect it. But if you are operating in gigahertz, the signal will see this T. The signal is coming from the left, and then this signal will see this discontinuity as an inductor connected a capacitor to here and an inductor. See, that's how the signal is going to see high frequencies. Then you cut your track, your PCB, you put a track cutting because there was a mistake in the design. Then in the high frequency you use the knife and cut it. Then you made sure that there is a separation. But when the high frequency signal, and then this line was 1 gigahertz clock, maybe or not 1, maybe say 5 gigahertz clock. Then what will happen is you made a cut here, but still signal will pass through because the signal will see it as a capacitor. See, it will be forming a capacitor. Again, if you are operating in 1 kilohertz, 10 kilohertz, fine. The signal will stop there. But in gigahertz, then it will see as a capacitor like this. Then again, if you are not terminating, some signal is ending here without any termination, it will see as a capacitor. See, 90-degree bend. So that is the reason the PCB design we are using 45 degree. We will not make a 90-degree bends. We already discussed it. Because if you are making 90-degree bend, again at high frequencies, it will see as an inductor, capacitor, inductor. So you will have distortions. So then these are the things we use for making also microstrip components. See, if you make one line, that is your track. Then if you can make a spiral like this, is an inductor. So you can make inductor like this using copper track. So this is an inductor. So then you can make something like spiral, and then you need a via that is connecting to the ground plane. So these all are inductor. So this is a circular spiral. This one is a square. So different shape you can make. Meander line. Then the equivalent is this one. So if you make an inductor resistor, this type of a combination, you don't need an actual inductor or resistor. You can use your PCB track. You can make something like this. This is an inductor. But then this is only applicable at very high frequencies, like RF, gigahertz frequencies, RF frequencies they use. Then capacitors, they also make capacitors something like this. See, one copper, then here they are making the separation. Again, interdigitated. See, so this is equivalent to a capacitor. So this is something like this. Then another interesting is transformer. See, people make transformer using microstrip antenna. So this is a simple transformer. So this is the primary, maybe this is a secondary. Or see, this is a transformer. or you can make one coil on the other side, another coil on the other side. I mean, transformer is easy because you know the two coils, both are coupling. So this is a very good example. So this is a multi-stage filter. So then this is a PCB filter. See, this is a filter. So this is a K connector, high frequency connector called K connector. So this can handle gigahertz. And then you are seeing only one track is coming, straight line. That track is ending here. Then they put some L shape like this, L shape like this, L shape like this. This is made of copper track. And then this is a filter. It's a passive filter. So see, so this filter is taking off 3.4 gigahertz. So this is kind of a notch filter. See, when it is experimentally characterized, you are getting a filter performance. It is removing some signal. So it's called a notch filter. So this is a passive filter. So again, this is, you can see frequency is 3.5 gigahertz. So at very RF frequency. So all these techniques are applicable to very high frequencies. But you should be knowing, though you are not designing RF, because when somebody gives you this one and asks what is this, then you should not tell there is some track and some art on the PCB, some artwork. Then you should be knowing, okay, this is something, you know, at least you should know what is the component. At least you can say this is some passive high frequency component. It could be a filter and or it could be an inductor, capacitor, but usually when it is coming from one end to another end means it is kind of a filter design. See, in your case you have designed using op-amp, active filter, but in RF you can design using passive. Then your question is, how can we design this one? So there are so many design software which will enable you to design these type filters. There you can input the frequency and then you can get this output, and then you can fabricate and then we can compare, it will be matching. Yeah, so if you want to make something L and C, something kind of this type of bridge combinations, and then you can make your PCB like this track. Then if you make like this, it will be equivalent of this one. So these are some very good references. Again, I give you lots of references at the end, so that if you are interested in some particular part, you can read further. And yeah, microstrip filters for RF by microwave applications. So this is a very good book. And high-speed circuit board signal integrity. Because these references are definitely, I am not going to ask any questions from these reference books. But then these I have given because maybe later you might be working at high frequencies, and then you can see some of the references when you want to read something. So that's the reason I have included. So I think maybe I'll stop here. So once again, one more announcement. So if Friday is a holiday, you can join in one of the labs happening this week. Because this week is anyway, it is a soldering practice. We will get some kit to learn soldering. I know most of you already learned soldering just for an experience. And second thing is, if your PCB you haven't submitted, then you have got an option to fabricate outside by yourself. And when you get your PCB back, you please send us a design, your design, so that we will verify this is your design. Anyway, I'll post it on Element.
About the 4-layer board, so if it's a ground plane or a BCC plane with normal capacitor, doesn't that include like parasitic capacitors or something?
Yeah, so so that one is not for bypassing.
Yeah.
This is for decoupling.
Okay.
So you are getting maybe from the regulator you are getting 5 volts. Then you need a big capacitor to store it.
Oh, okay.
Then maybe you can use this one. Yeah.
Oh, okay. So it stores across.
Yeah.
Professor, it's just okay. I submit my PCB on Saturday. I submit a bit late. I submit on Saturday on LMS.
Did you send me or you submitted on the?
On LMS on Saturday.
Then did you remove that file and submit it?
No, I just submit because it's not closed that time. So I don't know whether the tutor will do receive it.
No, I will not be doing the file session because it will be done by the head tutor. So I will check with him whether the updated version or anyway I'll write to you. You please email me.
I email you. Okay.
Because if already he made the panel, then we might not be able to replace it. If it's a big mistake or small mistake, you
No mistake. I mean, it's, I submit a bit late.
Okay, okay.
Oh,
That
yeah.
should be fine.
Oh, that's okay. I see.
Yeah, because if you are replacing the file, then it can get confused.
Oh,
You know
no.
what I mean? Yeah, yeah.
Oh, I see. I see.
Anyway, you please send me your student number.
Oh, my student number. Okay.
Yeah, I'll note it down.
Yeah, that's my student number.
Yeah, please
And
write
my
it down.
name. Yeah, I see.
So you please send me a mail.
Oh,
Send the mail that my student number is this one, my name is this one.
Yeah.
I submitted on Saturday.